Okay. Oh, you don't see anything. Here we go. Any questions? No questions? Okay, so we will start chapter 3 today. So we'll try to get through sections 3.1 and 3.2, just 2 sections, and so this will be enough to do homework, 2 and 3 and the quiz 3. Is it? Okay. So equations. I'm going to give you a few very silly examples and we'll try to solve them. Here's a very interesting equation. X minus 1 equals 0. I don't know if you want to be writing that stuff down at this point, but let's talk about that equation. Can we solve that equation? How do we go about solving that equation? Add 1 to both sides, and you get x equals 1, right? And that makes us very, very happy because 1 is a very nice number. We have that number on the number line, probably the first number ever used. We like 1. 1 makes sense, right? It is a real number. I can touch it. Here we go. I'm just touching 1. For those of you who don't see what I'm doing, I'm just holding a pen. Just 1 pen. So here we go. 1 is very tangible number. Makes sense, right? Real. Good? Confused yet? No. Excellent. Here's another equation. 2x minus 1 equals 0. Can I go about solving that one? Yeah, how would you do that? Add 1 to both sides. Good thing we have those wonderful properties of real numbers that, for every one there is another number that I can add. So x equals 1/2. Does that make us as happy as in the first equation? No, why not? You don't like 1/2? It is a fraction, but does 1/2 make sense? I'm about to pick up a half a page of paper because I cut it earlier. Here we go. Here, I'm holding a half. Half makes perfect sense to me. I know where 1/2 lives. It's right on the number line, right? Very happy. Makes sense. Real number. Makes me smile. Look at that. Didn't mean that to happen. Okay. Now I'm going to give you a very strange equation that might not make us as happy, but x plus 1 equals 0. How will we go about solving that equation? Very good. You see, he's just walked in and he's right on top of this thing. I know, and I gave you a hard time because of that. X equals -1. Well, how much sense does that make? Does -1 make sense? Yeah, because we've seen negative numbers for a while now, so we're pretty comfortable with that. But if you really think about it, that's a completely made up number. They just invented that number to solve this little equation. I'll shut up.
I'm missing 1 cookie now. I'm minus 1.
No, you're just missing a cookie. Now, see, like, if you're missing a cookie, like, nobody owes you a cookie. You have 0 cookies. No, that's +1 on another person. But your whole, like, you might have seen your bank accounts turn negative, things like that. But I should get you a cookie. So, but if you think about this, that's a made-up number. I cannot hold -1, right? -1 makes little sense. But we just said, let it be. Let there be negative numbers. Before bank accounts ever were invented, they just decided, it looks like we should probably need a negative number, okay? So they extended the number line to that left side of 0 to place all the negative numbers, but we're totally okay with that. Now, in 21st century, we're not freaked out by negative numbers. If we rewind our conversation a couple hundred years back, we might get a little freaked out by that solution. But it was just made up, but it's still real. We would get it. That right? To you, there was no difference in solving this third equation or the first equation. They feel the same to you. Do you agree with that? You're not being hung up on the fact that the answer is negative, or are you? You're totally cool with that, right? Okay, good. You know, I'm going somewhere with that. So, chapter 3. Come on, man. I gave you too much credit when you walked in. Here's another equation. We haven't done those equations yet, but x squared minus 1 equals 0. By the way, we'll do this equation officially in section 3.2. But can you still solve that equation? Okay, so you can plus 1, and then you get x squared equals 1. Okay, you want to square root both sides. So x equals plus or minus square root of 1. You have to remember that. So x equals positive or negative 1. And that still makes us happy because, well, we just solved a bunch of equations. Positive 1 makes sense. Negative 1 already makes sense. It was invented a while back or discovered. I don't know which one. But we're completely okay with that equation. Are you with me? I haven't gone crazy yet, but there is a purpose for that discussion. You wish that the rest of this class stayed that simple, don't you? Yeah. Now, here's an equation that might make us a little bit unhappy. Okay? X squared plus 1. Have I tried that before? Unhappy? That's kind of unhappy, isn't it? No? Yeah, all right. So we're just going to get rid of it. How would you go about solving that? All right, subtract 1. And now we're in a bit of a pickle, aren't we? We have a square on the left, and we know something about the squares. They produce positive results. But the thing on the right is negative. Do you agree with that? Now, do you know any real numbers, the one that live on a number line, such that if you square that number, it turns negative? We don't know any numbers like that, right? And even if I proceed with my taking square roots of both sides, that still won't help because I'm getting, you know, x equals plus or minus the square root of negative 1. And we spent first 3 weeks in this class talking about domain at some points, and we knew about square root functions. Don't like negatives under the square root. So we know this is not a pleasant situation. It's not a real number, okay? But we still like to solve this equation. We still would like to be able to list a solution in some kind of a meaningful way. So just like on this equation over here, where many centuries ago people went, hey, let there be negative numbers so I can solve this equation. A few years later, people said, well, let there be numbers so I can take square roots of negative numbers. They're not real. They're not on the number line. They're elsewhere. So we're just going to make up a whole new set of numbers that make this work. Okay? So this is called imaginary numbers. They're not real. We just imagine them. We cannot touch them. We cannot feel them. I cannot find them on the number line. I cannot go to Home Depot and ask for imaginary amount of lumber. They're made up. I cannot show you what imaginary number is. But I know some of its properties. So here's the story. We're making up a whole new family of numbers so we can solve certain types of equations. Meaning we can take square roots of negative numbers. That's what we'll try to do. So imaginary numbers. And complex numbers. So you might be feeling a little bit freaked out. That's how people felt many centuries ago when they saw negative 1. Just, well, what the hell, negative numbers. This is kind of the same thing. Made up a whole new number system. So here's a definition of imaginary unit. So this is the building block of all imaginary numbers, and we just decided to call it lowercase I. So that's a little number called I, and that number equals to square root of -1. That's how we define little I. Okay, so that's the definition. It has a wonderful property. If I square I, I'll get -1. So that's the situation where I'm squaring a number, it produces a negative result. So I is not a real number. It does not live on the number line. It lives elsewhere. I don't know if you want to know where I lives. If you want to send it a letter or a package, you need an address for I. I might, if I feel, if I'm still in a good mood by the end of today, I'll show you where I lives. You don't need to know that. You just need to know it's not on a number line. You're not going to find it on that pretty number line that you all know and love. But that's it. That's the definition of number I. Okay? Now, definition of a complex number. So complex numbers are of the form A plus BI, where A and B, both real numbers. Scroll up. So that's the definition of a complex number. A plus BI. A and B are both real numbers, so I'm going to write it like this. A comma B belong to the set of real numbers. Remember that fancy notation? So A is a real number, B is a real number, I is our imaginary unit. Is that okay? And in this definition, A, the number that doesn't have I next to it, we call A, is the real part. And B is the imaginary part of a complex number. Now I'm going to give you a few examples of a complex numbers. When you look at a complex number, you should be able to clearly identify the real part and the imaginary part. Okay? So example, 2 plus 3i. Here's an example of a complex number. 2 is a real number, 3 is a real number, I is that imaginary number. What is the real part here? 2. What is the imaginary part here? Just 3. Okay, so that's just the coefficient in front of the I. Okay, so 2 is the real number, real part, 3 is the imaginary part, and 2 plus 3i is a complex number. That's how it's written. There's nothing else I can do. I cannot add them. If this was 2 plus 3x, you won't be able to combine it, so it's kind of the same thing, right? Cannot do anything about that. So here's an example. It is a complex number. 2 is the real part, 3 is the imaginary part. How about this? 3 minus 7i all divided by 2. Is that a complex number? Yes. What is the real part of that number? 3 halves, because it's all divided by 2. So the real part, very good, is 3 halves. What is the imaginary part? Negative 7 halves. Very good, because I can look at this number and write it as 3 halves minus 7 halves I. 2 divides both portions. So 3 halves is the real part, negative 7 halves is the imaginary part. Good? Good. So that's still a complex number. How about 5i? Is 5i a complex number? Why not? Right, it's purely made up. It is imaginary number, but does it satisfy our definition of a complex number? Well, can it be 0? Can I think of this as 0 plus 5i? Yeah. So this is also a complex number where the real part is 0, imaginary part is 5. So when we look at numbers like that, they are called purely imaginary number, but they still belong to the larger set of complex numbers. So it is still a complex number, where real part is 0, imaginary part is 5. Okay? So it's still a complex number. If it doesn't have a real part, we can call it imaginary number, whatever you like. It's that. So it has to be in this form. Yeah, but both numbers are real, and since 0 is real, if we're missing the real part, we can always think that there is a 0 there. So that's another example. How about just 5? Is 5 a complex number? Sure. Doesn't have imaginary part. Imaginary part is 0. So it is a real number, but I can also think of this as a complex number with imaginary part 0. Okay? So every real number is also a complex number. So still a complex number it just has the real part is 5 and the imaginary part is 0. So this number does live on the number line, just doesn't have an imaginary part. So the set of real numbers is a subset of the set of all complex numbers. Complex numbers are much larger. Okay? So every real number is still considered to be a complex number. Is that okay? Now, just like with any other numbers, we can add, subtract, multiply, divide. And if you understand how to add, subtract, multiply regular real numbers, then you should be okay. And if you understand how to combine like terms, you should also be okay. If you understand how to FOIL, you're going to be all right when you do addition, subtraction, multiplication. Division is really tricky. When we're going to start dividing complex numbers, we have to get a little bit creative. But, so basic arithmetic. So, when you add, subtract, multiply complex numbers, you have to think of combining like terms, because the process is really the same. And 2, keep in mind that I squared does equal -1. Because a lot of times when you start multiplying complex numbers, the I squared will show up. You always can replace I squared with a -1. When you deal with complex numbers, you really don't want to see any powers of I. I should be always to the power 1. We will learn how to get rid of the powers of I. There is a little trick. But for now, keep that in mind. So let's do a few examples. I want to add 2 complex numbers. Let's say -2 plus 3i plus 1 plus I. So here we go. Sum of 2 complex numbers. So if you never seen I before, think of I as a regular variable. If this was x, would you be able to add those 2 expressions? Just think combining like terms. The parentheses are redundant because there is a plus there, so it's -2 plus 3i plus 1 plus I, and then just combine like terms. What do you get for the real part? -1, and what do you get for imaginary? 4i, right? So that's it. The real part is -1, the imaginary part is 4, right? And we're done. It's that simple. If you understand how to combine like terms, you're good to go. Any questions on that? Straightforward? Yeah. No, well, because it's not -1, it's square root of -1. So, right, because if I'm not squaring anything. So that's how you add. If I ask you to subtract -2 plus 3i minus 1 plus i, so just like with regular binomial operations, just open up the parentheses. So the negative sign will go in. We'll make it -1 minus I, right? So all your regular rules of arithmetic apply, and you combine like terms, you get -3 plus 2i, right? So the real part is -3, the imaginary part is 2. Okay? Does that make sense? So addition subtraction is really straightforward, just like combining like terms. Multiplication can get a little trickier. How about this? I'll take 3i times 2 minus 4i. So I'm multiplying these two numbers, 3i and 2 minus 4i. Well, I'm going to use the distributive property, just like with anything else. 3i times 2, what do you think that's going to be? 6i, so this is 6i. And then 3i times -4i, that will be -12i squared, right? Just by I times I is I squared. Are you okay with that so far? Now, that's where the -1 comes in, because we know that I squared equals -1, right? We know that I squared equals -1 by definition, so this becomes 6i minus 12 times -1, because I squared equals -1. The two negatives will give me a positive, right? So really the answer here is 12 plus 6i. The real part is 12. The imaginary part is 6. And that's it. Does that make sense? Is that good? Happy? Happy. Good. I like happy. How about this? 2 minus 3i times 4 plus, will be a good number, 5i. So I want to multiply these two numbers. So you would have to FOIL. You have two binomials multiplied together. So we FOIL. And we understand how to FOIL. 2 times 4 equals 8. 2 times 5i equals 10i. -3 times 4 equals -12i. And finally, -3i times 5i equals -15i squared. Just like you would do with any polynomials, if you had x instead of I, that's what you would do. Yeah, all of those, and I'm about to show you some examples. But yeah, all that applies. The only thing you just have to keep in mind that I squared equals -1. That's the only new real thing here, okay? So when I do that, I have 8. Then I can combine like terms. 10i minus 12i is -2i. And -15i becomes -15 times -1, which makes it +15. Right. Very good. So this is 8 minus 2i plus 15. So 23 minus 2i. Right? Is that okay? 23 is the real part. -2 is the imaginary part. Good? Questions? You okay? All right. You have a puzzled look. So it's not that scary. They're actually very friendly. Before you start dividing them. Dividing is a little nastier. But before we get to division, Shaq asked a question regarding those fancy little quick formulas. You know, formulas of quick multiplications, difference of squares, and those things. See what happens. If I take, let's say, 3 plus 5i times 3 minus 5i, right? You have two parentheses that only differ by sign in the middle, so feels like the difference of squares formula. I can multiply it really fast. Remember the difference of squares formula, a plus b, a minus b equals a squared minus b squared, that thing? So therefore I can just do this. 3 squared minus 5i squared, using the difference of squares formula. Or you can FOIL, you'll get the same thing. Now, what does 3 squared equals to? 9 minus 25i squared, right? And I squared equals -1, so this becomes 9 minus 25 times -1, which becomes 9 plus 25 equals 34, right? So we ended up with a real number. And this will happen every time. Every time you multiply two complex numbers that only differ by a sign in the middle, you will end up every time with a positive real number. Because the I will just get squared and will turn real. Okay? Do you remember when you first learned the difference of squares formula? And if you were in my class, I definitely told you that we do not have a formula for the sum of squares. A squared plus b squared cannot be broken down. Okay? But now, with the use of imaginary numbers, we can do that. A squared plus b squared actually equals to a plus bi, a minus bi. We needed that square root of a negative number in order to factor the sum of squares. Now, these two terms on the right, the two terms that only differ by a sign in the middle, are called complex conjugates. And every time you multiply two complex conjugates, you don't have to do anything else. You'll just take the real part, square that, take the imaginary part, square that, and add both results. So it will always result in a positive real number. This thing, no matter how hard you try, will turn in positive, right? Square, square with a plus in the middle, that's positive, right? Complex conjugates, right? Multiplying complex conjugates gives you real results. Are you with me on that? Okay. So let's do this example. Let's try to divide. Let's say I want to do this. How about 5 divided by 1 plus 2i? Which really is 5 over 1 plus 2i. Okay? Now this is something strange, right? You have no idea what the real part is and what the imaginary part is of that number. It's hard to tell. So we have to do something, right? We have to do something. Now remember, earlier, I gave you this example, 3 minus 7i over 2. And we had absolutely no problems with that. So when you have a real number in the denominator, life is really, really good. With me so far? So now ask yourself a question. Well, can you do some mathematical trickery here to make your denominator to just be a real number? Well, if I square it, it just... Now rewind it about a minute and a half, the phrase that I repeated 7 times. Multiply by its not opposite by, but complex conjugate. Because the product of complex conjugates results in a positive real number. So when you have your denominator, not, okay, Amanda, question? I think Amanda has a question. And Betsy has a typing stuff. Hello, type in your question. But anyways, while they're typing, or maybe they're not typing. Okay. But you see what I'm saying? If you multiply two complex conjugates, you will get a real number in the denominator. So this is just like rationalizing the denominators when you had square roots. We did the conjugate trick. Yeah, that's exactly right. Multiply by 1 minus 2i, because that is the complex conjugate. Very good. But now you have to keep in mind that you have to multiply both the numerator and the denominator by that. So that's how we make our denominator into a real number. So this is how we divide complex numbers. So let me, yeah, so it's always going to have the opposite sign, because then we'll get sum of two squares. 1 minus 2i, and in the denominator it's 1 plus 2i times 1 minus 2i. Now, you can FOIL the denominator, you can use whatever you like. What I like to do is for us to get comfortable with the sum of squares formula, because every time you multiply two complex conjugates, all you have to do is to take the real part, square that, and then take the imaginary part, square that, and add both halves. So, what is the real part in that denominator? 1, so it's 1 squared. Plus, what is the imaginary part? 2, so 2 squared. So that's your denominator, 1 squared plus 2 squared, which equals to, so 1 plus 4, which is 5. 5's canceled. So here we go. So 5 divided by 1 plus 2i equals 1 minus 2i. That's kind of freaky, but that just happened, right? We multiplied by 1, we know nothing changed, but this is a much friendlier situation. We can clearly see the real part, which is 1, and the imaginary part, which is negative 2. So, when dividing complex numbers, all you're really doing is rationalizing the denominator. You're making your denominator into a real number. That's all you really do. So division of complex numbers is equivalent, I'm not sure, to rationalizing I don't know, some spelling issues with me today. Right? So use complex conjugates. Yeah. Let's do a quick example. 3 minus 2i over 4 plus 5i. Some pretty large numbers there. Okay? So I'm trying to find the ratio of these two complex numbers, and it's really hard to just tell what it's going to equal to. It's almost impossible to just see the real and imaginary part. So the only option that we have is to multiply and divide by the complex conjugate of the denominator. Because we want the denominator to be real. We don't care about the numerator. Yeah, that's the best I could have done at that. Yeah, that R really kind of, yeah, it it went Greek on us there for a second. So yeah. But anyway, so multiply by the complex conjugate, which is 4 minus 5i divided by 4 minus 5i. That's how we divide complex numbers. We turn denominator into a real number. So that means in the numerator we have the product of 3 minus 2i and 4 minus 5i, while in the denominator we have a product of 4 plus 5i and for minus 5i. So we'll have to FOIL in the numerator, and in the denominator I can use my little formula, which just tells me to take the real part, square that, plus take the imaginary part, square that. So let's do the FOIL in the numerator. So it's 3 times 4, that's 12. 3 times negative 5 is negative 15i. Negative 2i times 4 is negative 8i. And negative 2i times negative 5i is positive 10i squared. Is that okay? So that's my numerator. Of course, I'll simplify it. Now in the denominator, product of two complex conjugates, so all I have to do is to take the real part, which is 4, square that, plus take the imaginary part, which is 5, square that. You know, whatever that is. Is that okay? Yeah, 41. But that's how you do it. If you FOIL, you'll get the same result. We just want to do it faster. So, in the numerator, we have 12 minus 23i. Now, what is I squared equals to? Negative 1. So positive 10 will turn negative 10, while in the denominator, it's 16 plus 25. And finally, when you combine like terms, you get 2 minus 23i over 41. Right? Yeah, because I equals I squared equals negative 1, so it will change that sign. Is that okay? And this is 41, by the way. That's a 4. Yeah, I don't know. My writing is a little Greek today, right? That feels like a Greek something. So what's the real part here? 2 over 41. What is the imaginary part? Negative 23 over 41. Which is not obvious at all just by looking at the number the way it was written. There are patterns, there are ways to just tell, but it's not obvious at all, right? I mean, but that's how you do that. That's how you divide complex numbers. You turn denominator into a real number by use of the complex conjugates. Is that okay? Maybe. Yeah, you'll practice. Okay, good. Now, a few more examples of imaginary number play. Let's say if I have something like this, square root of negative 16. Before we would say it's not a real number, which is 2. Hold, it's not a real number. But I can simplify that expression because now I know how to take square root of 16. I know how to take square root of 16. That's 4. I'm left with negative. And I also know how to take square root of a negative 1, which is I. So square root of negative 16 is just 4i. So I can do that now. I'm taking square root of a 16, that's 4. And I'm taking square root of the negative 1, that's I. Does that make sense? If I have some like this, square root of negative 8, do I know how to take square root of 8? Yeah, because that's right, because really this is what you're doing. You're going to split it up into 4 times 2 times negative 1, kind of. We know how to take square root of 4, that's 2. We know how to take square root of negative 1, that's I. And the square root of 2 will just stay behind. So 2i square root of 2. Or sometimes it's written as 2 square roots of 2i. They're the same. It's just some books like to put I in between the number and the radical, because if you write it like that, sometimes it feels like I. Well, it'll tell you. Yeah, don't worry about it. It'll tell you. Yeah, well, you got to read the little blue thing. Because sometimes if you write it, it might look like, it feels like it's the radical covers I as well, and that's never the case. You will not see I under the square root, basically. Well, I took square root of 4, that's 2, and I took square root of negative 1, that's I, and that 2 stayed under the radical. Okay? Well, we can, let's see, where's your book? Here's your book. So what are the complex numbers? Complex numbers. Let's see how your book writes it. Yeah, you see, they give you either I followed by the radical or radical followed by I. So the book really doesn't care. Here, right? It says no, this just happened to be negative in this example. So, but you see, it's either I in front of the radical or I behind the radical. You see, same thing here. 4I square root of 3 or 4 square root of 3I. Oh, it's all the way down there. Yeah, this thing. Can you see that? So you see, it's either I in the middle or I in the back. So I guess your book being very nice here. Now, when multiplying expressions like that, if you ask to multiply square root of negative 4 by square root of negative 25, and this is very important, the first thing that you have to do is to get rid of the negatives under the square roots. That's the first thing you do. Because negative 4I is what? 2I, and square root of negative 25 is 5I, so you'll get 10I squared, right? Which is negative 10. So you do that first. If you multiply before you take out the i's, you'll get the wrong answer. So it's really important when you're given problems like that, first take the i's out and then multiply. Is that okay? Otherwise, I mean, if I do multiply first, I'll get a positive answer. That won't be correct. Okay, so take out the i's first. So negative 10. That make sense? Now, the final thing that we need to talk about is how to raise I to a bunch of different powers. Because I want to, because you'll see things like, what is I to the power 11? What does that equal to? Okay, so we should learn how to perform that operation. So let's start doing some computation. So I to the power 1 equals I, right? Anything to the power 1 equals itself. Is that okay? And I to the power 2 equals negative 1. That is the definition. Is that okay? Now, well, let's see what is I to the power 3 going to give us. Negative I. How did you get that? You just knew that? Okay. Well, where did negative negative 1 come from? No, you're right. Because I cubed is same as I times I squared. Do you agree with that? By the properties of exponents. Now I know what I squared is. It's negative 1. So you get negative I. So what is I to the 4th? Just 1. Because I can think of I to the 4th as I squared squared. That's one way to think of I to the 4th. No, here's an even that's negative. No. But there is a pattern. The odd powers will be imaginary. It'll be jumping between I and negative I and negative I. While even powers will be real. Even powers will give us real results. We'll jump between negative 1 and 1. But for now, we have those first 4 powers. Well, how would you go to power 5? I to the power 5. Now I can always take I to the power of 4 out of that, because I to the power of 4 equals 1, right? So what do we have left? I. So we're back where we started, right? We're back over there, because now we can take those multiples of power 4 out of our exponents. I to the power of 4 times I squared. I to the power of 4 equals 1, so you're just left with I squared, which is negative 1. So we're back on top of that loop. Well, now without doing any math, can you guess I to the power 7? Negative I, because I to the power 7 is I to the power 7 is the same as I cubed, because you can always just subtract 4 from your exponent. So keep subtracting 4 from your exponents to get back to anything between 1 and 4. Okay? So if I do that with the power, let's say, I to the power, how about, what would be a good number? 71. I to the power 71. So all you really need to do is just divide 71 by 4 and just see what the remainder is. Because all you need is the remainder. Because the remainder will place you either 1, 2, 3, or 4. Yes. But what is the remainder when you divide 71 by 4? 3, right? Should be less than 4, right? 71 equals 4 times 17 plus 3, right? That's 68. So the remainder is 3. That's the remainder. So I to the power 71 is the same as I cubed. Because it's going to go through that loop 17 times. And it's going to go back to I cubed, which is negative I. All right? So this is how we're going to take I to weird powers. We're going to take the exponent, divide it by 4, and just take the remainder. Okay? Well, not yet. It will help us if you do the remainder. It's I cubed, and I know that I cubed is negative 1 based on my initial computation, right? I cubed equals negative 1. So my goal is to place it. What? Are you sure? So all you have to do, divide the number by 4, look at the remainder, that will place you in that initial loop. And if it divides evenly, then the answer is just going to be 1. Right? If you take I to the power that's multiple of 4, you're just going to get 1 out of that. Does that make sense? There's another way of doing that, which is more, because this process requires you to memorize that initial loop, I negative 1, negative I 1. You need to know the first 4 powers. Now, there is another way of doing that. I'm going to take I and raise it to whatever power you like. Give me a number. 77. And I'm going to ask myself, is this power odd or even? Odd, right? So if it's odd, every time that the power is odd, I will write it in that form. I'm going to borrow 1, and the rest is even. Okay? So I to the power 77 is the same as I to the power 76 times I. Is that okay? And then, since 76 is an even power, I can always write it as I squared to what? What is 76 divided by 2? 38, right? So you see what I did? I rewrote 76 as I squared raised to whatever's left. The reason why I'm doing that, because I know how to compute I squared. I squared is the easy one. What is I squared? Negative 1. So you end up with negative 1 raised to the power 38. Well, what is negative 1 raised to an even power? Positive 1. So it's just 1 times I, so that's I. Sneaky? So I'm trying to express it as a power of 2. Okay? Yeah, it just happened to be I. Right? Because again, if you take 77, if you do the early approach, you take 77 divided by 4, so the remainder is 1. So it's I to the power of 1. And if it's even right off the bat, I to the power of 122, you don't have to borrow 1. You can just write it as I squared to the power of 61 maybe, yeah? Yeah, half of that, right? 2 times 61, does that equal 122? So I squared is negative 1. Negative 1 to the odd power is negative 1. And we're done. So that's another way of doing that. Without doing the loop, without dividing by 4, you can always get I squared to whatever's left and get those results. Yeah, either way works. I like the second way because you don't have to memorize what I cubed is and I to the power of 4 is. But, I mean, they're both pretty straightforward. Is that good? Okay, well, those are imaginary numbers. Complex numbers, so that's your section 3.1. So let's do a little break, and then we'll do section 2.0. Okay, so that was section 3.1. Section 3.2 is mostly a review. It is solving quadratic equations. That's what section 3.2 is. The only addition to solving quadratic equations is that now we can do square roots of negative numbers. We have that I thing here. Okay? So quadratic equations. So a quadratic equation is an equation of the form ax squared plus bx plus c equals 0, where a is not 0. And a, b, and c are all real numbers. Okay? So there are 4 ways to solve a quadratic equation. Okay? One is by factoring. So if your equation can be factored, the life is really, really good. We use, your book calls it the zero product property. Which means if you have a product of 2 things, and the product comes out to be 0, the only way that can happen if one of those 2 things is 0. Okay, there's no other way. So if a product equals 0, then either A equals 0 or B equals 0, or both, but you got to have at least 1 0 in there. Okay? So for example, if we have something like x squared minus 4x equals 12, that is a quadratic equation, right? And we always hope that you can solve it by factoring. That will be the best thing ever, if you can solve your equation by factoring. But in order to do that, you do need to have 0 on one side of the equation. Otherwise, it doesn't work. So first step, move 12 over. Okay? So subtract 12 from both sides. You get x squared minus 4x minus 12 equals 0. And now try to factor that. Can we factor that? Yes. How? X minus 6x plus 2. That's right. We're looking for two numbers that multiply to negative 12 and add to negative 4, provided that there is no coefficient in front of x squared. If there is a coefficient in front of x squared, it gets a little trickier. Okay? But anyway, so now we have a product that equals 0, so therefore we can set each of those factors to 0 and then solve for x. So x equals 6 and x equals negative 2. Well, it's just, stop it. You just walked in. Yeah, well, we got back from break. Oh, shut up. I don't know if the mic picked that up. But I do have your... Did you guys hear what he said? What he said there? No, okay, so the mic didn't pick that one up, so I don't have you on record saying what you just said. He told me he hates me, but that's just my word. Anyways, we're just solving quadratic equations. Well, because you're interrupting me in the middle of the process when you walked in a little late. That's just impolite. So, is that okay? When things can be factored, the life is really, really good. So, the other, I'm not gonna do any more examples of that. You've done this in your other classes. You know how to factor. You have plenty chances, plenty chances to practice that. The second technique is the extracting the square root. It uses, your book calls it, well, the principle of the square root. It uses the principle of the square root that suggests if x squared equals k, then x equals plus or minus square root of k. So when you do that square root, you always have to remember the plus or minus. Okay? Example, and that's what you saw earlier today when I wrote x squared minus 1 equals 0, but here's an example. I know x squared minus 5 equals 0. Okay? So the question is, can we put our equation in this form, where one side is a square, the other side is a constant? Can we do that? Yeah, we can add 5 to both sides. So x squared equals 5. Then x equals plus or minus square root of 5. And we're done. Okay? These are the two answers. Positive square root of 5, negative square root of 5. If I have something like this, x squared plus 16 equals 0. How would we go about solving that? Yeah, subtract 16 from both sides. X squared equals negative 16. So x equals plus or minus square root of negative 16. Yeah, so this is plus or minus 4i. Right? Both of them work. If you take 4i, you square that, you'll get negative 16. If you take negative 4i, you square that, you still get negative 16. Is that good? Now, we can take this technique a little bit further. What this expression really means is blah squared equals constant. Doesn't just have to be a single x. Could be some expression squared equals a constant. So if that's the case, then blah equals plus or minus square root of that constant. And then you can go ahead and solve whatever it is you like. Okay? So here's an example of what I'm trying to say here. So again, x does not just have to be a single letter. It could be some other expression. So for example, if I have 2x minus 3 squared equals, 4. So that's what I mean. You have blah squared equals a number. I can still do that square root thing. Okay? So that means whatever's under the square, 2x minus 3 equals plus or minus the square root of 4. Just using that principle of the square root. Almost, but not 4, 2. Yes, you're right. Because really what this means, your right-hand side is plus or minus 2. So that gives you two equations. 2x minus 3 equals 2, and 2x minus 3 equals negative 2. Right? Because your expression can either be 2 or negative 2, which is two equations. Two nice, friendly, easy to solve linear equations. So I can go ahead and solve them. Right? The first one, add 3 to both sides, you get 2x equals 5. Divide by 2, x equals 5 halves. Right? While the other one, you get 2x equals 5. I'm sorry, not 5. 1. You add 3 to both sides. 2x equals 1. X equals 1 half. Is that okay? So again, if all your variables under the square, we can do that. If the other side also had an x, we won't be able to do that. We'll have to do something else. But if you have everything under the square equals a number, you're good to go. Is that good? What about this example? 3 times 2x minus 1 squared plus 5 equals, how is it going to get bad? This is the worst case scenario, equals 4. Oh, we're going to love that. Okay? I can still do this little technique. But first, I need to isolate my squared term. I have to get 2x minus 1 squared by itself. So what do I have to do? Subtract 5 from both sides. So you get 3 times 2x minus 1 squared equals negative 1. Then what? Divide both sides by 3. Very good. So we get 2x minus 1 squared equals negative 1/3. Is that okay? All right, so now we have everything under the square equals a constant. So what do we do now? Square root, throw in plus or minus. So 2x minus 1 equals plus or minus the square root of negative 1/3. Okay? And you really have to do a lot of work about that negative 1/3, because there are a few things that are wrong with it. First of all, we see a negative under the radical, so we should replace it with an I. So I can say it's a plus or minus I over the square root of 3. I took square root of negative 1, I got I. The square root of 3 remained to be the square root of 3. Now we have a radical in the denominator, right? That's kind of shaky. Well, because I did this. You can do that, but it's, I just took the square root of the numerator and the square root of the denominator. That's what I did. So the square root of the numerator is I. It's the same thing as that. There's just no reason to write that. They're the same. Because the square root of 1 is 1, so they're the same. But can you leave radical in the denominator? What? No. What do you do about it? Yeah, multiply by square root of 3 by square root of 3 to rationalize the denominator. So really what we end up with is plus or minus I square roots of 3 over 3. So that's what my right-hand side is. Is that okay? So that means I have two equations. 2x minus 1 equals I square roots of 3 over 3. And the other equation is 2x minus 1 equals negative I square root of 3 over 3. And again, you can place that I anywhere you like. Well, let's just keep it in the numerator. Okay, how do we go about solving that? We need to solve for x. Let's just focus on the first equation. How do you solve for x? Right, add 1 to both sides. So 2x equals what? I square roots of 3 over 3 plus 1, right? How do we do that? We need a common denominator, don't we? So it's same as 3 over 3. I square roots of 3 over 3 plus 3 over 3. So I can say that 2x, and I'm going to write it like this. 3 plus I square roots of 3 over 3. Is that okay? But it's still 2x. How do we get rid of 2? Yeah, divide both sides by 2. So over 2 over here, and divide by 2 over there. Right? Now, dividing by 2 when it's a fraction is same as multiplying by 1/2, right? So instead of multiplying by 2, I can say, well, this is the same as just multiplying by 1/2, so why don't I just write that? It's this times 1/2. So they're just going to turn my denominator into 6. So x equals 3 plus I square roots of 3 over 6. Is that okay? We'll do the same exact steps on the other side. The only difference is going to be negative in the middle. All right? So if I do that, again, add 1 to both sides. So we're going to think of 1 as 3 over 3. So this is 2x equals 3 over 3 minus I square root of 3 over 3. So that means 2x equals 3 minus I square root of 3 over 3, just as before. And then divide by 2, which same as multiplying by 1/2. So you can say times 1/2 times 1/2. So 2's cancel. X equals 3 minus I square root of 3 over 6. So these are the two solutions. And notice how both of these solutions are complex conjugates of each other. The only difference in these two solutions is the sign in front of I. Do you agree with that? That's the only difference between these two solutions is the sign of the imaginary part, which makes them complex conjugates. Right? Remember complex conjugates? Only differ by sign. And that's always going to be the case. If you get a really complex number like that with an I part, you're always going to get its complex conjugates. Complex roots, complex solutions, common conjugate pairs. We'll make that official when we're going to look at bigger polynomials, but here's that. Is that okay? All right, so that's the second technique, when everything is inside the square, and then you just square root both sides. The third technique is completing the square. So that's second time we're going to talk about that thing. We talked about completing the square when we're dealing with circles. Remember that? Now we're going to talk about it again. So let's see, let's take a good example when we complete the square. Okay, well, here we go. 2x squared minus 1 equals 3x. So there are a few things that need to happen in order to complete the square. Because what I'm trying to get at, I want when I complete the square, I want my equation to look like that. So all the variables inside the square, while the other side is just a constant, whatever we just did. So I need to do everything possible to do that. So in order for me to do that, I have to move all the constants to the right, all the variables to the left. That's going to be the idea. So first, subtract 3x from both sides. So we have 2x squared minus 3x minus 1 equals 0. So we're trying to solve this equation. You should always think about factoring it. I don't think it's going to work. Right? No? Yeah. So let's try to complete the square. In order for us to do that, we don't need that plus 1. Move 1 over. So that leaves us with 2x squared minus 3x equals 1. Okay? Now, do you remember when we were dealing with circles, there's a certain thing that you have to do in order to complete the square. So, but the first thing was variables on one side, constants on the other. And this is what we just did. Now, the second big thing, in order for us to complete the square, we really don't like having anything in front of x squared. That's just bad news. So we want to get rid of that 2 in front of the x squared. And the way we do that, we're just going to divide both sides by 2. I want to get rid of that coefficient. I want just to have x squared, period. So when I do that, that gives me x squared minus 3/2 x equals 1/2. So the second step, divide both sides by the coefficient in front of x squared. Okay? Are you still with me? Now we're going to complete the square. How do we do that? What do we need to do to complete the square? Anyone? Oh, you just no idea. Now you just guys throwing stuff at me. No, there was a comment there. How do we complete the square? Should be in your notes from like week 1 when we played. No, not yet. I want to add something here. So my left-hand side becomes a perfect square. That's what I want. Remember how we find that magical piece that we're missing? Come on. Second, all right. So let me see. Who said that? Yes. You take the constant in front of the x, you half it, and you square it. That is the missing bit. Well, yeah, it's in your notes somewhere. Who went what? All right. Let me do this for you. Where are our lecture recordings? From week 1. Oh, what am I doing? It's probably here. It's easier this way because we have that. So, modules. Week 1. Sections 1, 1, and 1, 2. Oh, yeah. Is it going to play? Oh, maybe I should click on that. Here we go. It'll take me a while to locate that. Is this a circle? Oh, I think I'm right on the money. Here we go. Look at this. I'm going to turn it up. Oh, I know the, oh, come on. Where's the sound? Anyways, first week, we talk about completing the square. I drew pretty pictures for you. Do some voodoo. You see that? Completing the square right there. Um, I don't know what's with the sound. Because the computer is silly. It actually thinks that this microphone is a speaker. So it's, I'm just telling you, you have to go back and watch some of the old lectures. That's what I'm suggesting. Okay? Because we went over that. You need to know how to complete the square. I told you that I'm going to come back a few times in this class. I'm trying to close this window. So, completing the square. I'm going to go through this fast because you guys have to go back and relearn that. But what we do, we take the term in the middle. We're going to half it. So it's 3/2 times 1/2. And then we're going to square it. So we're taking 3/4 and we're squaring that. And that's what we're going to add to both sides of this equation. Okay? So the left-hand side automatically becomes x minus 3/4 squared, because now it's a perfect square, while the right-hand side is whatever 1/2 plus 3/4 is. So 1/2 plus 9/16. I need to figure that one out, which is x minus 3/4 squared. What is the common denominator on the right? 16, is that right? So when you add the right-hand side, you get 17 over 16. So go back to week 1. Lecture, so Wednesday lecture. Review completing the square. It will come back again. Yeah, because I can. I'm not answering any more questions because you're going to have to go back to week 1 and review that. But this is the third step to complete the square.
In the main problem, the green and red problem. That's where you got that from, right?
What?
The green and red problem at the top. Like,
Yeah, it's still here.
so you just like made that, you just completed the square.
Yeah, so I added this magical term to both sides of the equation. Yeah, because you have to keep the equation. So that's why 1/2 turned into 17/16 over here. Right? You have to know how to complete the square. So that was the third step. Third step was complete the square. By adding, I'm doing the common denominator. Completing the square by adding the missing piece. And we do that missing piece by taking the constant in front of x, dividing it by 2, and squaring it. That's what's missing. So if you go back to that Wednesday's lecture, there was a pretty picture of me drawing rectangles and squares, and then we're realizing whatever's missing is that little thing. So we take the constant in the middle, you divide it by 2, square that. That's what you add to both sides. So when we get to this point, we can finish this problem, right? We're going to take the square root of both sides. We'll get x minus 3/4 equals plus or minus the square root of 17 over 16, right?
Is that the answer?
No, the answer should be x equals a number. We're not done yet. I cannot take square root of 17, but I can take square root of 16. What is the square root of 16? So this is square root of 17 over 4. To solve for x, we're just going to add 3/4 to both sides. So we get x equals 3/4 plus or minus square root of 17 over 4, which is 3 plus or minus square root of 17 over 4. We can list our answers in that form. That's acceptable. So the bad news is you have to know how to complete the square. The good news is you rarely use this technique unless you specifically told to use that technique. Because if you're given options, you're never going to use this. You're not going to solve the quadratic equation by completing the square. Okay? Because there's a fourth technique. There's a fourth way, and that's the way we all know and love when solving quadratic equations. So the fourth technique is quadratic formula. Because when you're stuck, when the factoring doesn't work, you're really going for quadratic formula. So, does anybody remember the quadratic formula? And should be everybody, right? So what is the quadratic formula? Yeah, that's okay, close enough. That's what, yeah, that, well, all right, good. Can you write it down? All right, good. That's what counts. Now, this formula is how you complete the square. This formula comes from completing the square. So I'm going to derive this formula, and don't write anything down, but you're going to help me. I'm going to complete the square. I'm going to solve this equation by completing the square. So don't write anything down, but you're going to help me. So in that little list of steps, solving equations by completing the square, what was the first thing we had to do? Yeah, variables on one side, constant on the other side. So subtract c from both sides, right? We get ax squared plus bx equals negative c. So that was the first step. What was the second step? Didn't I say don't write this down? Don't write this down. You don't need it. It's in the book. You can watch this. I want you to talk to me. What is the second step? Divide both sides by coefficient in front of x squared. So yes, divide both sides by a. So the left-hand side is x squared plus b over a x equals negative c over a. Right? So that was the second step. Now the third step, we're going to start completing the square. The way we do that, we take the term in the middle. We're going to divide it by 2, right? So multiply by 1/2 and then square it. So that's what we're going to add to both sides, right? So it's b over 2a squared plus b over 2a squared. Right? That's how we do completion of the square. You take the term in the middle, half it, square it, add to both sides. So automatically the left-hand side is x plus b over 2a squared. That's just your formula, right? The square over some formula. It does that for you. While the right-hand side, let's work that one out. Negative c over a plus, what is b over 2a squared? How do you square a fraction? b squared over 4a squared, right? So what is the common denominator there? 4a squared. So what do I need to multiply the first fraction by? Right, 4a over 4a, right? So then what do we get? We have 4a squared in the denominator. Here I have b squared. negative 4a times c, so that's 4ac. Right? So we have this now. We have a perfect square equals that thing on the right. So now we can take the square root of both sides, right? And when we do that, we get x plus b over 2a equals plus or minus the square root of b squared minus 4ac over 4a squared. Is that all right? Now the square root of b squared minus 4ac is just going to stay that, but I can do the square root of the denominator, which is just 2a. Right, square root of 4a squared is 2a. Now subtract, solve for x, so subtract b over 2a. So that cancels. X equals negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. So we're done, right? That's our formula. That's exactly what it is. It's completing the square in one move. Okay, because we just did all the hard work for every a, b, and c. So we're just going to be that every time. So this is why when you ask to just solve this quadratic equation, you will never complete the square. You'll go straight for that if it's not factorable. Unless I specifically tell you, here's the problem, solve by completing the square, show your work type of thing. Okay? Which I still might do. But here's the formula. This is how we use it. So an example, let's say 3x squared plus 2x equals 7. So I want to try to solve this equation. And I'm not saying how I want you to solve it. I just want you to solve that. So in order for us to start solving quadratic equations, I really want to see 0 on one end, because I just hope it might factor. Okay? So that's what you're thinking is, you always hope that things factor. And the factoring only works if you have 0 on one end. Now, can you factor that equation? I mean, can you factor that expression on the left? Which is fine. You can still factor, right? Even there is a coefficient. Remember how we do that? We look for two numbers that multiply to this product, which is negative 21, and add to 2. So probably not. I don't know two numbers that multiply to 21, negative 21, and add to positive 2. So it's not going to factor. But even if you can factor that, but it takes you a long time to factor, you kind of stuck on factoring, just move on to quadratic formula, quadratic equation. Because the quadratic equation says that so it says negative b first. Well, what is b in this equation? 2. So negative 2 plus or minus square root b squared, which gives me what? 4 minus 4 times a, which is 3, times c, which is negative 7, all divided by 2a, so 2 times 3. Right? So that's the setup. The rest you just have to compute that. Negative 2 plus or minus the square root of 4 plus what? 84? Is that right? 4 times 3? Is that right? Yeah. So we end up with negative 2 plus or minus square root of 88 over 6. Okay? Not yet, because you always want to try to simplify it further. Can you take square root of 88? No. But we can split 88 into a product of a perfect square and something else. 88 is 4 times 22, is it? And what is the square root of 4? 2. So we get negative 2 plus or minus 2 square roots of 22 over 6. Is that right? Well, I have to simplify 6 and both of those 2's. Okay, so technically I have to factor 2 out of the numerator. That'll give me negative 1 plus or minus square root of 22 over 6. And now I can reduce that. 2 and a 6. Right, I took both of the 2's out. And 6 becomes 3. So that would be my final answer. Negative 1 plus or minus square root of 22 over 3. Yeah? So again, we realize that I have a 2, 2, and a 6. So I can factor 2 out of the numerator and reduce it with a 6. Because 6 divides both, or you just divide both by 6. But you cannot just cancel 6 with one of those 2's, but not the other. Good? Right. You've done that before. Quadratic formulas. Again, the only new thing, if you get a negative under the square root, don't freak out. Take the I out. That's really what it is. Okay, so when you solve these types of equations, there are 3 things that can happen. You can get 2 real solutions, like that. 2 pretty real solutions. Well, not pretty, but real, right? You can get 2 complex solutions. We had an example somewhere. Didn't we have an example? When we got 2 complex solutions, like here, right? You can get 2 real solutions, 2 complex solutions. Yeah, but well, I mean, like, really. Okay, how about we get 2 real solutions? We got no real solutions here, right? But also can get just 1 real solution. There is a case where you can get only 1 real solution. And let's see, how about 4x squared plus 10x plus 25 equals 0. And by 10, I mean 20. Here we go. Okay? I can do this by factoring, or if I use the quadratic formula. So again, I have a 20 in the middle. So by the quadratic formula, I'll get negative 20 plus or minus the square root of 20 squared minus 4 times 4 times 25 all over 2 times 4 using the quadratic formula. Negative b, all that. So let's try to compute that. What is 20 squared? 400. And what is 4 times 4 times 25? 400 over 8. So 400 minus 400 is 0. So I have a square root of 0, so the whole square root really is irrelevant now. So we just left with negative 20 over 8, which is negative 5/2. One solution, right? And really the number of real solutions is determined by whatever happens under the square root. If you end up with a 0 under the square root, you're going to get only 1 real solution, just 1. Yeah, it's always going to be real. If you get the thing with the I, it always comes with a friend that is complex conjugate. So it's always 2. So you can either get one real solution when you get 0 under the square root. You can get two real solutions if you get a positive number under the square root, like in this example. Or you get no real solutions, as that's when you get a negative under the square root, so you introduce the I and stuff. So we have a special name for that expression under the square root. We call it the discriminant. And discriminant literally equals b squared minus 4ac. It is the expression under the square root. Okay? And basically it will come down to this. If discriminant is greater than 0, if you get a positive number under the square root, you will get two real solutions. That's one. If the discriminant equals 0, so the square root goes away, you're going to get exactly one real solution. But if discriminant is negative, we end up with a negative under the square root. That means I shows up, so no real solutions. So then we have no real solutions. Both solutions will have I in it, and they will be complex conjugates of each other. They'll just differ by a sign in the middle. Yeah. Is that okay? I want to do one more example. I have about 5 minutes. So, equations of quadratic type. And this is the tricky part, and this is kind of important. Sometimes you get an equation that's not really a quadratic equation, but it sort of looks like one. What I mean by that is, consider this example. X plus 2 over 3 squared minus x plus 2 over 3 minus 12 equals 0. So here's an equation like that. Doesn't look, I mean, it's not a quadratic equation because it's not really, ax squared plus bx plus c, but it follows the quadratic equation pattern, where you have something squared, then same exact expression without a square, and then just a constant. So it kind of looks like that, right? Something squared, same thing not squared, and then a constant, right? I'm talking about the x here, right? Only x is squared. So you have something with the variable squared, and then the same exact thing not squared. So what I can do here, I can say that, well, let's make it look quadratic. I can make a substitution. Introduce a new variable, whatever you like to call it. Let's say u. We can say let u equal whatever that expression is, x plus 2 over 3. Because I can do that. I'm going to replace every x plus 2 over 3 that I see in that equation with this new letter u. So if I do that, I'll get u squared minus u minus 12 equals 0. So I'm replacing a very complex term, very complicated term, with a single letter. And now this thing looks quadratic, doesn't it? Now just can we solve for u here? Right, it's a very simple quadratic. I can factor that. u minus 4, u plus 3 equals 0, right? Factors very nicely. So that means u minus 4 equals 0, or u plus 3 equals 0. And then you solve for u, so u equals 4, u equals negative 3. Well, I need two numbers that multiply to negative 12 and add to negative 1. So it has to be minus 4 and plus 3. If I had a plus u, then it would be plus 4 minus 3. So I just solved for u, but I have to solve for x. That's the goal. Well, what does u equal to? Yeah. Well, but mostly u equals x plus 2 over 3. That's what we define it as, right? That's u right there. So I'm going to substitute back. And that gives me x plus 2 over 3 equals 4, or x plus 2 over 3 equals negative 3. So then I can solve for x. Right? So I ended up with two much simpler equations. So how do we solve for x? Multiply by 3. So you get x plus 2 equals 12. And then subtract 2. X equals 10. Is that right? And over there, multiply by 3, you get x equals negative 9. And then subtract, x plus 2 equals negative 9. And then subtract 2, x equals negative 11. So x equals 10, x equals negative 11. And you will see many examples like that when you have an equation that's not quadratic, but it follows the quadratic pattern, where you have something squared followed by something that's not squared. So you can make a substitution. Okay? That looked like a quadratic. It followed that quadratic pattern. Okay, good.